Good day and thank you all for listening. My name is Brendan Waffle and I am with XOS, a manufacturing company of X-ray optic and full beam systems for research and industrial applications. We are based in Albany, New York, and my current role for XOS involves working with XOS's various original equipment manufacturing industrial customers and universities, developing new projects and assisting in the designs of optics and beams for future research and applications. Here you have it, the mini beam. Just wanted to give a quick introduction of the mini beam to give everybody an idea of what the system looks like moving forward. You can see we have a polycapillary X-ray focusing optic mounted to a low-powered microfocus X-ray source. Coupled together, these components make up a powerful yet compact mini X-ray beam generator that has the ability to be a solution for a wide variety of applications. The original concept of the mini beam came about in a joint project between XOS and JPL with NASA. A system with the same basic concept as the mini beam was actually on the Mars Perseverance Rover that was launched in late 2020 and successfully landed on Mars in early 2021. Both the launch and landing were recorded live. If you haven't had a chance to watch it, I'd highly recommend. You can see here the main mission goal is to discover evidence of past life on Mars, and the X-ray optic microfocus source combo will play a key role in accomplishing this mission. We'll talk about that a little bit later. Specifically, the mini beam system was integrated onto JPL's Pixel, which is on the rover's robotic arm. Yes, there is a mini helicopter on the rover, and no, our optic is not on it. Since the Viking lander in 1976, almost all landed Mars missions have had XRF instrumentation on board. However, the capabilities of these instruments did not allow for the precision and X-ray intensity required for accomplishing the Perseverance mission goal, which is finding evidence of prior life on Mars. You can see here the prior XRF capabilities really only include the ability to perform bulk composition sample analysis. This is due to the fact that large area analysis on the scale of 17 millimeters in spot size was the best prior capability. This level of precision does not allow for fine analysis for analyzing differences between geological structures on the surface of Mars. Not only that, but the intensity provided by an optic will dramatically increase the speed at which analysis can be performed, which is essential when mapping a relatively large surface area. Mars 2020 rover requirements and challenges. You can see here some of the requirements for the optic source system. The first requirement being achieving fine spatial resolution for measuring elemental variation on the sub-millimeter scale. The second requirement being intensity. As you can see, the measurement speed of this system is impressive. The speed in which this system performs analysis will allow the rover to map many different surfaces across the various landscapes of Mars. Here are some challenges. Some of these may seem trivial, some not. The desired spatial resolution for the pixel system was on the scale of microns. 100 microns was the requirement to be exact. Another challenge being the spatial restrictions for sending an optic and X-ray source to Mars. The system needed to be very compact in order to mount correctly to the rover's robotic arm. Power is another hot commodity on the Mars rover, hence the decision to pick a low-powered microfocus X-ray source. The system had to be built around the polycapillary X-ray optic, so a microfocus source was decided upon as the performance of an XOS X-ray optic is optimal with the micron source spot sizes. The source needed to be low powered because, of course, the production and storage of power on the rover is extremely limited. Last but not least, reliability and durability. Yes, to get to Mars, the X-ray optic and beam had to survive the transportation from Earth to Mars, which we can all summarize as strenuous. The system that was designed to meet these requirements and overcome these challenges was, in fact, a system very similar to the mini beam. X-ray optics on Mars. Pixel is one of 7 instruments that are present on the Mars Perseverance Rover. In the image on the right, you can actually see what the polycapillary X-ray optic and microfocus source looked like before they ended up going to Mars. This is a mirror image of the system that is currently performing analysis on Mars. The X-ray optic is the long cylindrical steel-colored component in the right-hand side that is pointing down towards a preliminary sample. The X-ray optic is there to provide the ability to reveal the geochemical fine structure of the Martian surface, and we can see some example results on the image in the bottom right-hand corner. These are some results of preliminary testing and analyzing some different geological structures using the micro-XRF system in which the source is only a milliwatt-powered X-ray generator. Now we're going to talk about polycapillary X-ray optics specifically. Polycap optics are not a new technology per se, but the advancements in manufacturing and design capabilities have come a long way. You can see by the late 1990s the latest generation of polycapillary optics was developed. These optics have the ability to focus the spot of an X-ray source down to the size of a single micron. This ability provides a bright X-ray spot that has intensity gains in the thousands of orders of magnitudes greater than a traditional pinhole collimator. The image on the left shows what the optic looks like before it is packaged into an enclosure. The actual optic is made of glass and is therefore relatively fragile, as you can imagine. The enclosure is meant to serve as a protection for the internal glass optic and allow for simplistic mounting or integration of the optic into an X-ray system. These optics are now used across a wide variety of industries for many different applications. Some of these we will mention later on. Polycapillary X-ray optic. How does it work? So there are a couple of different types of polycapillary X-ray optics that can be integrated to an X-ray source like the mini-beam. The diagram on the top shows a focusing polycapillary optic, and the diagram on the bottom shows a collimating polycapillary optic. Each of these optics is made up of hundreds of thousands to multi-million capillary channels in which the X-rays enter the optic and then bounce off the walls of the respective channel that the X-ray originally entered until the X-ray reaches the optic output, at which point the X-ray is either focused to a micron-sized spot for a focusing optic or collimated for a larger spot to form a quasi-parallel beam using a collimating optic. The focusing X-ray optic can focus down to 5 microns with an exceptional amount of flux generated from the optic's large effective collection solid angle, and the collimating X-ray optic can generate a beam size as large as 25 millimeters with a flux density up to 5 times greater than that of a typical pinhole collimator. The energy in which these optics best perform is less than 50 keV. Above 50 keV, the X-ray optics struggle to contain large amounts of these high-energy particles inside of the channels. The monolithic structure of these optics also help to make the glass optics surprisingly robust. At the end of the day, it is a glass optic. Fundamentals of polycapillary optic structure. Here we can see a very cool close-up picture showing what the actual individual channels of the optics look. When examining an optic by eye, it basically looks like the image on the left, and you can't actually feel any channels or indentations with your fingers. This is because the channel sizes are in the micron range. Moving to the right, you can begin to see the channel's individual hexagonal shape and a surprising amount of open area, up to 80%. This is important because the larger the open area, the more X-rays that can be captured by the optic's channels. The surface roughness is also minimized to prevent X-rays from terminating due to an incorrect trajectory caused by an irregular shape or deformity of the channels. If you remember, the X-rays bounce off the channel walls, so surface roughness can decrease the transmission efficiency of the optics. Lastly, the X-ray optic shape or profile is controlled down to the single micron range to allow for precise design and prevent an irregular channel shape, as an elliptical shape is essential for maintaining the X-rays in their respective channels and reaching the optic output. Integration of a polycapillary optic to an X-ray tube. When it comes to polycapillary X-ray optics, the source size is a very important factor. The smaller the source spot size, the greater the optic transmission efficiency and the greater overall intensity or performance. You can see the graph on the left shows the optic transmission efficiency as it relates to both energy and source spot size. It's clear the smaller sources have higher transmission efficiency. The alignment of the optic is another important factor when it comes to overall performance of an X-ray optic. An X-ray optic can only perform as well as the optic is aligned. If the alignment of the X-ray optic is off, the performance decrease can be significant. The graph on the right shows how a position change of merely a few microns causes a 2% change in output beam intensity, and I'll emphasize that's just a few microns. Mini-beam optic and alignment features. Here we have it. Finally going to talk about the mini-beam specifically. When it comes to the mini-beam, the most optimal optic alignment is achieved in-house before the beam ever leaves our doors. There's also stability testing to ensure the focal spot is stable in position. The X-ray optic mount can be seen in the center of the image near the input end of the optics. The optic mounts were designed to allow for the easy exchange of optics, so that a single mini-beam could be used for various types of applications. The alignment features of the optic mount allow for fine-tuning the optic alignment or even exchanging the optic out, as I mentioned earlier. This process is incredibly simple, in which the user can loosen a couple of set screws and then turn a couple more screws to shift the optic in the desired direction to find optimal alignment. You can see on the optic mount that there is a tiny cylindrical rod that is sticking out the top of the optic mounting fixture. This is the simple primary filter slot, in which filter material can easily be exchanged depending on the material and thickness needed for the particular application. The mounting and alignment features, coupled with a seamlessly integrated primary filter slot, really make the mini-beam incredibly user-friendly. Not only user-friendly, but also very adaptable depending on the project or equipment's needs. Mini-beam source features. Now we're going to talk a little bit about the low-powered micro-focus source that is coupled to the XOS Polycapillary X-ray Optic. As mentioned, the source has a very compact design to allow for the integration of the mini-beam into systems that have limited space or would like to have a portable setup. The source has the high-voltage power supply and controller built right into the chassis. Specifically, this source is a 12-watt source, and the interface for communicating with the internal controller is a USB connection that can communicate with a PC for simplistic ramping. Also, you might have noticed there is a fan located on the side of the source, as the source is kept temperature controlled through the use of a single fan for air cooling. Cooling systems don't get much more simpler than that. Since the optic mount so easily allows for the optic alignment, the source can actually be detached from the mount, allowing the user to send the source out for repair or replacement while keeping the optic and mounting fixture intact. So the fixture can easily be attached and the optic realigned to the repaired or replacement source. This source was selected to be coupled to our X-ray optics not only for the reasons listed above, but for one of the biggest reasons that we have discussed prior, the relatively small source size. The source spot size is around 300 microns, providing reasonable performance coupled with an XOS optic. I say reasonable because ideally source spot sizes less than 100 microns are best, but this source was chosen based on its overall capabilities, not just the source spot size. Even though this is a low-powered source, the focal spot size and intensity produced by the mini-beam as a whole is exceptionally impressive. Here we have a table that shows some specific performance and spot size capabilities of our polycapillary X-ray optics for the mini-beam. The table on the top shows our polycapillary focusing optic specifications, and the table right below shows our polycapillary collimating optic specifications. The top row of the first table shows the corresponding output focal distance, also known as working distance for the optic. You can see we have a few options with various output focal distances ranging from 4 mm to 50 mm. Next, you can see some output beam intensities at 50 keV and 0.2 microamps, using the silver K-alpha energy of 22.16 keV. This is the impressive intensity I was talking about given the low power nature of the source. Below that, you can see the focal spot size measurements for each of these optics, with the 4 mm OFD optic having a focal spot size of 15 microns at the silver K-alpha, the 10 mm output focal distance having a 25 micron spot, and so on, up to a 100 micron spot at an output focal distance of 50 mm. Onto the collimating polycapillary optics table. Notice the output beam diameters range from 4 mm at the smallest diameter up to 15 mm at the largest beam diameter. Below that, we have the corresponding intensities for each of these optics at the same power setting as mentioned for the previous table and using the same silver K-alpha energy. The smallest output beam diameter with an intensity of 5 times 10 to the 5th photons a second, up to the largest beam diameter having 3.2 times 10 to the 5th photons a second. Customization options for various sources. A polycapillary X-ray optic can be coupled to different types of sources as well. The optic and its alignment/mounting fixture can be modified so that a source different from the standard mini-beam source can be used in its place. Depending on the application or system requirements, a source with different characteristics may prove to be a better option as compared to the standard mini-beam design. In this case, the polycapillary optic and its mounting/alignment fixture can be coupled to the desired source. Even a custom X-ray source can be integrated with an XOS X-ray optic through collaboration with the XOS team. Mini-beam application, halo reduction for micro-XRF. What allows the mini-beam and polycapillary optics in general to perform true micro-XRF is the halo reduction capability. You can see in the upper left corner a piece of copper plating with different micron-sized holes. The scale in this image is 0.5 millimeters. Then below that we have intensity mapping images for a standard optic, and then to the right of that a halo reduction optic of the same spot size. The conclusion that can be made is that the halo reduction optic dramatically reduces the effects of excited elements outside of the focal spot, allowing for a much more precise measurement. You can especially see this when looking at the smaller sized holes. Even though there's a hole in the copper plate, the intensity from the non-halo reducing optic is still quite high. The graph in the upper right corner verifies this conclusion in that the copper fluorescence intensity does not significantly drop when the focal spot is in a hole as compared to the halo reduction optic. Halo reduction is a critical factor that makes polycapillary X-ray optics extremely beneficial when it comes to performing micro-XRF. Mini-beam application, micro-XRF. Here are some pictures and diagrams showing some of the preliminary data that was taken with the mini-beam-like source for the JPL pixel system. As mentioned, the system is being used for elemental mapping requiring fine spatial resolution. In the large picture showing the elemental mapping, you can see how it's critical to have fine spatial resolution so that we can distinguish differences between geological structures. Like with the top visible image in the elemental map, the system allows us to see a distinguished line labeled unconformity, in which there is a clear separation between silicon and potassium sediment. On the right, this diagram is showing the different geological structures that the pixel system needs to be able to distinguish between in order to perform its job successfully. These structures range from an unabraded surface to a linear abraded surface or an unabraded surface with scattered or sparse features. This is just one example of how mini-beam technology can be used to perform micro-XRF. Northwestern University, artwork scanning with mini-beam. Here we have another very cool application, at least I find this very cool. Northwestern University has integrated a mini-beam system into a custom, highly versatile, mobile macro-XRF scanner for situ analysis of painted works of art. The system's goals include identifying the material makeup of the various pigments that were used to produce early period or archaic works of art in order to identify the impacts of aging so that the works of art could better be preserved in the future. Another goal includes identifying the early period materials that may be associated with fake or forged artworks, or artworks that may have been restored in some manner. The mini-beam is perfect for such an application as mobility, spot size, and performance are all essential in completing the analysis of various artworks both rapidly and efficiently. Mini-beam conclusions and the higher power Flex-Beam option. The mini-beam is a compact yet powerful X-ray generator for advanced material analysis. The mini-beam is an optimal solution for X-ray systems requiring compact, low-power solutions. By coupling an XOS polycapillary optic to this microfocus source, a microfocus spot on the scale of microns can be generated with a large amount of flux density, creating an intense, bright X-ray spot. Beyond the performance capabilities, the design of the mini-beam allows for multiple optic types and sources to be used, allowing unprecedented capabilities for an X-ray source optic combo. This is also incredibly user-friendly given its simplistic design. The Flex-Beam, which is also offered by XOS for those who need a more powerful X-ray beam solution. This is a 50-watt source instead of 12 watts and therefore offers a more intense focal spot. This system also uses a microfocus source for optimal performance and offers many of the same great features available with the mini-beam, including the easy exchange of sources for different applications and service, and a simplistic optic mounting mechanism for exchanging or replacing optics. The Flex-Beam also has a built-in safety shutter as an extra component for safety and an integrated multi-position primary filter wheel capable of holding 8 different filters. Customization capabilities. If an even higher powered source is needed, a polycapillary X-ray optic can be integrated into that system as well. For those that need the most intense X-ray spots, the optic can be mounted to larger watt sources that may even have smaller source spot sizes, down to 5 or 10 microns. Some of these sources include a rotating anode source, a sealed kilowatt source, or even a custom X-ray source. When it comes to XOS polycapillary X-ray optics, it's worth reaching out to the XOS team to learn about our capabilities with your specific project or system requirements. Thank you all for listening. I hope you enjoyed this presentation learning about the new XOS Mini Beam and what XOS has to offer regarding its custom polycapillary X-ray optic solutions. Looking forward to hearing your questions.